So in this problem, we are looking at a quarter falling down into a well, and we are given the total time of the sound of the splash, which means we have 2.4 seconds from when the quarter is let go of to when that person hears the sound of the quarter hitting the water. Now, it doesn't just mean kinematic motion down to the surface of the water of the well. It also includes the speed of sound of air. So you have to take into account that the particle quarter moves down some distance the depth of the well, but then the sound has to come back up. And so we've sort of got two portions of that 2.4 seconds that we have to take into account. So the first thing we want to do is draw a picture. So we can just draw a little well on the ground, and the bottom of the surface is just water. And so what happens is we know t total to be 2.4 seconds. The sound of the splash is heard 2.4 seconds later. And we also find that the speed of sound in air, right, how fast the sound moves, you can say v of s, velocity of sound, is 340 meters per second. In any direction, there's no acceleration of the speed of sound. The speed of sound just moves at 340 meters per second. So now, what else do we know? Well, we know acceleration of gravity is negative 9.8 meters per second squared, which we'll use. This is just, you'll know. So what we need to do is find some way to describe the kinematics of the quarter falling, as well as the sound wave coming back up. And so the first part asks how far below the top of the well the surface of the water is. So how deep is the water? And so we're just going to call this distance d. It's also, you could call it delta x. And we're just going to go with d for this problem. So what happens is the quarter falls down, distance d. So what we can say is that delta x of the quarter, delta xq, is equal to negative d. It is the negative distance because it travels down, and we're going to assign that to be negative y and positive y to be the up direction. Once that particle goes all the way down and travels distance negative d, the sound wave comes back up. And so we're going to call that delta x sub s, delta x sound, change of position of the sound wave. Now that travels distance positive d because it goes up distance d. Now this sign is very important because it takes into account the fact that these two objects go in opposite directions. Their motion is not in the same direction, and so we can't just set it equal to each other like we normally would. Normally you would just say, like in previous problems, the change in position of the quarter is equal to the change in position of the sound wave. But since they move in opposite directions, it becomes a little bit more convoluted, where one of these terms, this position of the quarter, it actually travels a negative distance, and the sound wave travels a positive distance. Now, well, what can we say? We know that distance d is equal to delta x, but we can say it's equal to delta x sub s, which is equal to delta xq, right? These change in positions are equal in magnitude, but their signs are just a little flipped. And so since we know that delta x sub s is equal to delta xq, we can see that, oops, this was a mistake. Oh, Lord. Okay. So, in this problem, we are given a quarter falling from rest at the top of a well, and you hear a splash 2.4 seconds later. And it says, what is distance d? Right? And distance d is just a magnitude of the distance between the surface of the well and the water towards the bottom. And what we know is that the total time of travel for the particle to fall and the sound wave to come back up and hit our ears is 2.4 seconds. And so we know that the quarter goes down distance d and the sound wave travels back up distance d. Now, how can we relate the motion of the quarter to the motion of the sound wave? Now, this is a little bit tricky because we have to think in terms of the magnitude of position change, right? Because the quarter travels in the negative direction. If we were to assign the positive and negative y-axis, the quarter travels in the negative direction, and the sound wave travels in the positive direction. So if we really want to equate these, we have to take this negative vector, this negative position, this velocity vector, and flip it. So if we were going to say that delta x of the quarter equals delta x of the sound wave, well, this just isn't true because delta x of the quarter is negative d and delta x of the sound wave is positive d, and you can see negative d is not equal to d. So we know that we cannot just directly equate their motion because the change in position of the quarter is in the negative direction. So what we actually have to do is tag on a negative in front of that. And now we see we have like negative, negative d, and those negatives cancel out, right? And you end up just getting d equals d. You can see that this is true. So all we have to do when we have this sort of opposed motion is one of those changes in position is just going to end up being negative. We're just going to tack a negative on there. And this is probably the most confusing part of this problem is just understanding that when you have a change of position in two opposite directions, if you multiply one of them by -1, now you can set them equal to each other. And this equality is going to be very similar to what we use in a lot of these other problems on this homework set. So we know we can describe the position of the quarter, a quarter in free fall, with an initial velocity of 0. We have the general equation, b sub 0t plus at squared. And so when we plug in all of the variables, well, v initial is 0 because it says a quarter is dropped from rest. So what is acceleration? Well, right at 1/2 there. That's my bad. Acceleration is going to be -9.8, and divided by 2 times t squared. Now, what is this time? We had time total of 2.4 seconds, but is this time total? It's not. So in this problem, we have to divide that time into two parts, where there is the time it takes the quarter to fall, and then there is the time it takes the sound wave to come back up. So we end up deriving this equation where the total time is equal to t of the quarter plus t of the sound wave. And so we have to acknowledge that the total time is 2.4, and so both of these two times, the time of the quarter and the time of the sound wave, both of them are less than 2.4, and they add up to be a total of time of 2.4 seconds. And so when we talk about the motion of the quarter, we always refer to TQ, the time the quarter falls, and TS refers to the time the sound wave travels back up. And making that distinction is crucial in order to keep your variables separate. Right? We never want to confuse the properties of the quarter with the properties of the sound wave. Otherwise, nothing is going to work out. Those two objects are separate. And so we have to make sure that anything we connect between them is really shared between them. Now here we have as simplified of an expression as we can get for the position of the quarter. Now we can find a position of the sound wave equation. Now we're going to use the same general form, v initial t plus 1/2 at squared. We know that our v initial is 340 meters per second. And that is multiplied by time, and this is time with the sound wave, since we're working with the sound wave now. And the sound wave has no acceleration. It's a constant velocity. So that's all we have for the expression of the sound wave's position. And so we found these two, and so we can go back and we can look at our original equality between the two changing positions. We saw that negative delta xq was equal to delta xs. So we can go ahead and plug everything we have in. So we have negative. We have a double negative there of 9.8 divided by 2 times tq squared. And that is equal to 340 t sub s. Now let's drag this up a little bit. So we have a double negative, and so that becomes a positive. And we end up with 9.8 over 2 times tq squared equals 340 t sub s. And we can go ahead and change that 9.8 over 2. Just change that really quick down to just 4.9. 9.8 divided by 2 is 4.9. And so now we're getting pretty close, but we still have tq and ts. Those are two different variables. We can't just use them as though it was just one time. They're two separate times. So we have to figure out what equation do we have that can relate tq to ts? Well, back up here we found total time equals tq minus ts. So we write this down here, total time equals tq minus ts. Sorry, plus ts. Those two times added together equals t total. And so if we were to subtract the time the quarter moves from both sides, we would get the time of the sound wave is t total minus tq. In other words, 2.4 minus time quarter. And now we have an expression for the time the sound wave takes, right? In terms of the time of the quarter. And so we can take this and plug it back in place of ts. All right, let's give ourselves a little more space. So now we have 4.9 tq squared equals 340. And we are going to substitute in this new expression in terms of tq. Now you can see we have some algebra to do. We have 4.9 tq squared equals 340 times 2.4 is 816 minus 340 tq. Now this is a quadratic equation, which we're going to have to solve using the quadratic formula. So what that means is all of these variables have to get onto one side of the equal sign. And so we're just going to move everything to the left. We're going to have 4.9 tq squared plus 340 tq minus 816. All right, and so this is equal to 0. All right, so, all right. So plugging in these A, B, and C into a quadratic equation calculator gives us a time of quarter movement of 2.32 and negative 71.71. And we know time cannot be negative, so this is clearly not the right answer. It's also very large, much larger than 2.4. So we go, it's kind of not on the right scale. But 2.32, well, it's on the right scale. It's right around 2.4, and it's less than 2.4. So that means if we were to look at our t total equals tq plus ts, we see that t total was 2.4, and tq we found to be 2.32 plus ts. And subtracting 2.32 from both sides, we find that the time of sound equals 0.08 seconds. And so we found a reasonable result for both times. Now this is just finding the time of the motion down and the sound wave traveling back up. This doesn't tell us yet how deep the well is. And so for that, we go back to, oops, I need to do that. We go back to our original position equations, position of Q, position of S. And so we can pick either one of these two position equations to find, the total distance d. We could plug in TQ to this equation or TS to this equation. Now I'm going to choose TS because that is a simpler equation. It's just 340 times TS, right? So delta X sub S equals 340 TS. And so I can just take 340 times 0.08, and I'm going to plug that into my calculator, and I get 27.2 meters. That is how deep the well is. Now this is a little bit inaccurate, most likely due to some kind of rounding error in our quadratic, our quadratic equation. I believe the precise exact answer is 28.2 meters. We're just 1 meter off. A little odd. Um, all right. So we found our time of Q. And we remember from above that we found the total time to be time of Q plus time of S. So the total time is the motion of the quarter plus the motion of the sound wave. And remember, time total was 2.4 seconds. And we found time of quarter to be 2.32. And we can just do plus TS, time of the sound wave. Now all we have to do is subtract 2.32 from both sides to find that T sub S equals 0.08 seconds. Now, we've found a reasonable result for both times. They both follow all the equations and situation we have. So now what we have to do is take that time and convert that into a distance of the well. If we go up to our problem, remember we get distance d, delta x. So we can actually find delta x of q or delta x of s. The magnitude of either of those is going to tell us the depth of the well. So I'm going to use delta x of q. And so delta x sub q equals negative 9.8 over 2 times sub q squared. So to evaluate this, I'm just going to plug in times sub q of 2.32 squared. And so we find that delta xq equals negative 26.4 meters. We got a negative. That is because it travels down. Now we want the magnitude. We just want the distance. And distance is a magnitude. Displacement is a vector with direction. And this is our displacement vector, but we just want a distance. We just want a 26.4 meter deep well. That's going to be our answer. Deep. 26 meter deep well. Now, we found how deep the well is, but now it says for part B, if we neglect the time of the sound travel, and we assume that the entire 2.4 seconds is used for the quarters movement, well, what percentage error does that introduce in the depth calculation? So what that really means is if time of Q changes to the full 2.4 seconds, now we see that we're probably going to get a different result than when we use 2.32. So we're just going to directly use that equation again. Delta x sub q equals negative 9.8 over 2. And instead of using 2.32, we're just going to use 2.4. And so this is kind of like a rough estimate because in reality, there is a sound wave. Not that whole full time, that whole 2.4 seconds is not all being used for the quarter to fall. And so for our precise calculation, we have to account for the speed of sound. But a lot of times in physics, we're just going to do these rough estimates. And so this will give us a delta x sub q of 28.2 meters. And you can see that this is pretty different from our 26.4 meters we found before. So how do we find the percent error? Well, we have the definition of a percent error is your change in results. So your results, accurate result minus your result estimate. So the difference between the two results, and you're going to divide that by the result accurate. So which is the accurate result and which is the estimate? Well, 26.4 accounts for the sound wave. It's more accurate. That's going to be our accurate result. And 28.2 is our R estimate. So this equation, don't forget we're multiplying by 100 to get a percent. This is what we're going to use. So all we do is take our R accurate of 26.4 minus 28.2 over 26.4. Just multiply by 100. And so we're actually going to end up finding, in this situation, we're going to find negative 7%. Really, we just say this is a 7% error. We just take the magnitude of that error. We don't care if it's plus or minus. We just care about how far, the number of percent, the magnitude of the percent. So this is a 7% error. And so that's kind of considerable. It's not enough that, you know, in the purposes of this class, we usually won't account for sound. But, you know, if you were really doing this in real life for a job or something really was on the line, there was a lot of money on the line, you definitely would have to take into account the speed of sound. All right, so in this problem, we found the depth of the well by finding how long it took the quarter to fall, and how long that sound wave went back up. That told us how deep the well was. And then we were able to estimate a less accurate depth and compare our results to find that we have a 7% error from our estimation. All right.